Good morning. So, everyone, can you hear my voice?
Yes, I can hear your voice.
Okay, thanks. Okay, let me start with the share screen. Maybe I use the desktop. Okay, let me start. Uh, Before we go into the chapter 3 today, I would like to provide you an information about the recording of our video links. I create a Microsoft Word files and put on the video clips. You can get the file from the shared drive that I share with all of you. And I think you see in the files, you can have the link for the class that we have a discussion on last week on Tuesday and on Thursday, right? So if one of you would like to have a look about this, to check the discussion we have done before, so you can get to the file in the video clip, I mean in this folder. Okay, I try to update this video clip link for you every Thursday and every Tuesday and Thursday after class. For today discussion, I would like to proceed on the chapter 3. And in this chapter, I think we are talking about the free vibrations. And before we start, I would like to provide you a big pictures in with the real building or actual building. Once you formulate, before you formulate, right, you have to try to make what we call the physical modeling, find a way to model your actual building by using a physical modeling and put the mass on each floor connected by the spring or by the stiffness, so that this physical model can be great or will be very good representing your actual building motion under the wind or the earthquake or any excitations. After you have a proper physical model, you apply the law of physics to change the physical model to a mathematical model, where what we have discussed so far, you can see the physical model that lead to the mathematical model in our case are, how do you say, is the two type of the physical model that we are considering. The first one is about the continuous model. The second one is the discrete model. The continuous model lead to the partial differential equations. On the other hand, the discrete model can lead you to the ordinary differential equations. And it looks like we prefer the discrete model where the computer software, like the commercial programs that are available in the market, can dealing with easily. Therefore, we focus on the discrete model, and the mathematical model that involved is about the differential equations ordinarily. However, such ordinary differential equations contain the form like this, right? Let me start with the mx double dot plus, I'm sorry, the damping term, cx dot plus k x equal to f of time t. In this case, M is a matrix, X is a vector, MCK, every terms are either the vectors or the matrices. It contains many parameters inside, and it contains many degree of freedoms. And this is what we call the ordinary differential equation system, where you have many numbers of the differentials in these equations, and you need to solve them simultaneously, since all of these equations are what we call the depend from each other. Once is depend on each other as an interaction between the equations, and you cannot solve one by one equation. You have to solve them every equation in the same time or simultaneously. So we leave this for the second part of this course, where Dr. Chatpan will come to discuss with you about the multi-degree freedom system. This is the MDOF. Okay. With me, you are expect to have a discussion in this form with me. Mx double dot plus Cx dot plus Kx equal to force function ft. In this case, you see, only the m is just one parameter, right? It's not a matrix. It's just a scalar. X double dot is also the acceleration, but it's not a vector. It's just the 1 degree of freedoms. Okay, just the time functions. It's contain only one x. It's no unlike the previous matrix system where you have x1, x2, x3, but this time you have only one x. To solve or to study this single degree freedom system, in terms of mathematics, we found to get this differential equation, the solution of this. Let me. What you have to do is to solve this second order differential equation. Second order ordinary differential equations. The x of time t as a solution of these equations becomes something like this. If you have studied about the differential equations and mathematics of this before, I do believe you have to understand this. The solution, the general solutions, a complete solution of the second order differential equation take the form of the summation of the two parts of the solution themselves. One is called homogeneous part and another called is a particular part. Okay, therefore the complete solution of the x of time t become the summation of the homogeneous part of x, xh, plus particular part of x, that is xp. Okay, where the homogeneous solution, the xh is, let me draw this, right? Where the homogeneous part is a solution of this. cx dot ht plus kx ht equal to 0. This is the solution of the same equation, except the force function ft equal to 0. If you assume that the force is 0, the solution you obtain will be the homogeneous part of the solution. And then we obtain what they call the particular part later on, right? The reason we have to learn or to discuss about the free vibration today, because as the mathematics is an important part of the solution. To get the complete solution, you need to get the free vibration first. Why free vibration is the important part of the solution? This is because when you solve the differential equation, what you have to do is to perform integrations. In this case, your differential equation is a second order. Therefore, you have to perform the integration 2 times. When you have done the integration with your equation, you have learned in terms of mathematics, right? The integration 1 time you create one arbitrary constant. Therefore, if you want to obtain the solution of the second order differential equation, you are talking about 2 arbitrary constants in your solution. To taking care of these 2 arbitrary constants, the part of the solution called the homogeneous solution will do the job for you. That's why we have to solve the equation when the force equal to 0. This is the explanation of mathematics. In the view of mathematics. But in our case, when I assume there's no force acting on the system of the building, this has the physical phenomenon called free vibration. The vibration of the building, even though the force is stopped, right? When the wind blow, your building start to shake, or the earthquake excite your building start to shake. After the earthquake gone or the wind gone, you see the building is still shaking, and then it stop. Okay, the way that the building is still vibrate after there's no force acting on them, we call free vibration. The vibration without any excitation, or the vibration without any external loading. Okay, that's why today we will discuss equation number 1. The case of the free vibration, sometimes we refer to the case where you apply the initial conditions, like if I knock on the building, at the top of the building there's some impact loading on it, and you remove the force, it starts to have the initial velocity, and that will make your building to move freely without any external force. But the energy is start from the initial velocity you input to the building. Similarly, if I apply the initial displacement, let at time t equal to 0, move your top of the building 1 meter away, and then release. We will check back and forth like this, right? This is the same phenomenon. That is a force, is a free vibration. In this case, the governing equations that explain how your building move under the initial conditions, like the initial velocity, initial displacement, or the vibration remaining after you remove the loading, those are described by equation number 1. You see equation number 1. mx double dot c plus cx dot plus kx equal to 0. There's no external force on the right-hand side. Okay? In terms of mathematics, if this equation is not the differential equations, the solution is very, very simple, right? If you want to make the left-hand side equal to 0 as the right-hand side, you have to input the displacement x equal to 0, the velocity x dot equal to 0, and the acceleration x double dot equal to 0. This will definitely make your left-hand side, the equations of the three terms become 0, equal to 0. But that solution is trivial. Of course, they can make the equation equal to 0, left and right-hand side, but we don't care about this solution. The solution that you're building doesn't move at all. We don't care. Okay? So we will focus on some other solution of x dot and x double dot that can make this equation equal to 0, even though there are the movement in the building. I'm saying that sometime in this equation, number one, sometime when x equal to a certain function, x dot equal to certain function and x double dot equal to certain function, I can make this equation on the left-hand side to be 0, even though x is not 0. And we will see today that we can find the x, the solution of equation number one, which is not 0 function, but can make equation number one to be equal to 0. Okay, so let me define some terms. Sometimes we're starting to call each term with some meaning of that. The first one is the pink one that I draw. It's called this term as the inertial force, inertial term or inertial force. The second term, this one is the damping term, the damping force, and the last term on the line is the stiffness. Is the stiffness term, or some people call it spring force, restoring force. There's some many names of this term: spring, stiffness, or restoring. Okay, but the first term mainly is about the inertia. The second term is about the damping. Okay, these three terms, in fact, the summation of three of them need to be equal to the right hand side. This one, in fact, we are talking about the external force or external excitation, but today we will assume this force equal to 0, and we will find a solution. This is a discussion of free vibration equation number one. Okay, and this might be one of the physical model of equation number one. You can imagine you have the mass M connected with the spring K and the dashpot C to the fixed support. Okay, and if I apply the initial condition, for example, I clamp the mass and force them to move to the right direction 1 meter, and then I release, the mass will try to going back to the ball, to the support, to the wall, right? And it start to move back and forth, back and forth, back and forth, like that. To get the solution of equation number one, let me go back equation number one a bit. Equation number one, to make the solution X that satisfy the left and the right hand side equal to 0, with intuitive, I think you might thinking about a function of X, the time function of X, where the derivative of X dot and X double dot take the same form with X. See, if you apply the function of X like a t square or t power 3, sometimes you see the derivative will take another form, right? If you apply the polynomial function of time t to the solution X, the problem is you cannot make the three term, the summation of the pink, the blue, and the red become 0. But if I can find another functions of time t where the derivative will take the same form with the original function x, that might be possible to make the three terms, summation of them will cancel themselves and become 0, equal to the right hand side. And such a function in this world is the form as in equation number 2, the time exponential function. The time exponential function e to the power a constant s multiplied with time t is one of the possibility. This is because if you try to perform derivative of the exponential function, your result will be the same form of the original, right? For example, if I perform derivative of x from equation number 2, my x dot become the term like this: s x 0 e to the power st, and x double dot becomes something like a s square x 0 e to the power st, like this. The interesting is the form of the e to the power st doesn't change when I perform the derivative. Therefore, it's very possible to make this form of the function, time function, the summation of them becomes 0 on the left hand side. Okay, we will start by introduce equation number 2 into equation number 1. And when I do so, you see, you got equation number 3. And because x0 e to the power st is not equal to 0, okay? x0 is not 0, otherwise your solution is trivial. E to the power st cannot be 0. Therefore, if I divide the whole equation 3 by x0 e to the power st, you will get as in equation number 3, right? ms squared plus cs plus k equal to 0. M is the mass, C is the damping coefficient, K is the stiffness. The unknown now to me is only S. Okay? And equation number 3 has its own name. We call this as a characteristic polynomial equations. To obtain the S, this is not news to you, right? It's just the quadratic equations. You can get the solution of S easily, but before we write down the solution of S, let me define the 2 more terms for you. One is called omega squared equal to k over m. Another is precise, this one. equal to C over 2m omega. These two terms we define is not, actually you not introduce the new parameters to the system. Remember your system you have is, the parameters you have is M, C, and K, three of them, right? But now we try to make, to have only two parameters instead of three. That is about omega and psi. And these two parameters, omega and psi, they have their own physical meanings. Omega is about the vibration frequency, circular frequency of your system. You will see later, once you obtain the solution. The omega, we explain how your building move back and forth, back and forth. If your omega is very high, it's moved like this. If your omega is very, very small, it's moved like that. Okay? The damping or the psi is one of another parameter that control how fast, how slow your building will stop to zero. This one is related with the damping, called psi. Okay, so let's introduce omega square and psi as in this equation, these two equations. And if I introduce these two parameters into equation number 3, you see now you obtain equation number 4. S squared plus 2 omega psi S plus omega squared equal to 0. And now let me obtain the quadratic solution of this equation. And the solution of the two roots, okay, since this is S squared, so you should have two solutions for S. The two roots of S are minus psi omega plus and minus square root of omega psi omega square minus omega square, or is equal the last term on the equation number 5, right? Omega multiplied with the minus psi plus minus square root of psi square minus 1. And since the roots of the characteristic polynomials contain the square root of psi square minus 1, the problem is about this term. There is a problem of this. Whether or not these green terms become negative number, become 0, or become a positive number. Okay? There are three possibilities in which the term psi square minus 1 in this square root can be negative number, can be 0, or be a positive number. These three possibilities will make the vibration of your building change totally. The way that the building moves, the way that the building will respond to the initial conditions will totally different if a psi square minus 1 take the different form of the value. For example, it's become negative, it's vibrate like this. If it's become 0, maybe it's vibrate like that. If it's become positive, it become vibrate like another movement. We will study the three possibilities today. And the first possibility of the solution is, and look like this, the case that the most of the civil engineering structures belong to is the case of precise square minus 1 less than 0. Most of buildings, most of bridges falls into this category where the precise square minus 1 is a negative number. Okay, we have the name of this. When precise less than 1, precise square minus 1 will less than 1, 2, or be a negative number. In this case, we call such system, the system having the damping, we have the name of this, damping ratio. Precise is the damping ratio. If your precise or damping ratio less than 1, we call your system as the underdamped system. With the underdamped system, the solution of your S need to be a complex number. Since inside the square root, you have a negative number, and such value or such quantities, we make the number to be what we call is the imaginary number, right? And that's why we can have the S to be a complex number. And since your S will take a two roots, your S now become what we call the complex conjugate. You have S from equation 5. Once you assume that precise less than 1, you can have the solution as in equation number 6, in which S become omega multiplied with minus precise plus and minus I multiplied with the square root of 1 minus precise square. Let me provide you that this I is nothing. It's just the square root of minus 1, right? Okay? And this make the term of S become a complex conjugate. You have S1 and S2. You have two solutions. S1, you use the positive sign, right? And the S2, you use a negative sign. You see, both of them have a common, a real part, but they have a plus and minus of the imaginary part. If you have a common or share the same magnitudes of the real part and imaginary part, but the sign change from plus and minus in the imaginary part, we call these two numbers as a complex conjugate. And this is the case of underdamped system. In terms of mathematics, your two roots of S become a complex conjugate, right? As in the right-hand side, I draw for you S1 and S2. If I introduce this S1 and S2 into equation number 4, the solution of X become as in equation number 7. Okay, you can prove yourself, but the idea is very simple. You look at the pink letter that I have the handwriting, right? I will write down that X of time t equal to X0 multiplied with the alpha 1 e to the power S1t plus alpha 2 e to the power S2t. And I introduce S1 and S2 into this equation and manipulate somehow. I will change everything to equation number 7. Okay, where now alpha 1 and alpha 2 will change to by somehow by some term arrangement to A1 and A2 instead. And equation number 7, you see the two term of exponential. The first term is the e to the power ix, and the next, the second term is e to the power minus ix. This is a sine and cosine function already. Let me introduce one more parameter for you, omega d. Omega d is the omega multiplied with the square root of 1 minus precise square. Okay? And if I introduce omega d into equation number 7 and use the Euler's equation as in equation 9, I can change equation number 7 into equation number 10. See, equation number 10 now, your solution x of time t become an exponential of e to the power minus per sine omega t multiplied with the x1 sine omega dt plus x2 cosine omega dt, where x1 and x2 are constant determined from the initial conditions. Okay? And if you not prefer the form of equation 10, some textbook, they prefer the form what they call the phase angle form. They replace equation 10 by equation number 13 by introduce the big X and the phase angle as in equation 11 and 12 into, and you obtain a very compact form as in equation number 13 as a solution. Okay, see, either you use equation number 10 or equation number 13, both of them contain two arbitrary constants. Equation 10, you contain x1 and x2 as your arbitrary constant. Equation number 13, you contain the big X and the phi angle as the two arbitrary constant for you. Both of these two equations, both of the arbitrary constant has to be determined from the initial conditions of your system. For example, if your building is start from introduce one initial displacement, 1 meter initial displacement, and let it go with the initial velocity equal to 0, you move back and forth like this, right? If I put like this and release, if we move like this initial condition of 1 meter for the displacement and 0 for the velocity at time t equal to 0 are the two conditions that we use to determine the x1 and x2, or the big X and phi in equation number 10 and number 13 respectively. Okay? So if I assume that the initial conditions at time t equal to 0, when we're talking about the initial condition, the word initial mean t equal to 0 is the starting time. At time t equal to 0, if I assume that the displacement of my system is x0, the velocity is x dot 0. In this case, if I use equation number 10 as my solution, I will introduce x, okay, equation number 10, look at equation number 10. At time t equal to 0, you can write down x0 equal to e to the power 0 x1 sine of 0 plus big X2 cosine of 0, right? And I think you can have x0 equal to a big X2. Am I correct? That's why you can have this. The first equation in equation number 14. Similarly, if I perform derivative of equation number 10, okay, let you do it yourself, okay? You just find what is the x dot t, right? By perform or conduct the first derivative with respect to time t on equation number 10, you should obtain x dot. Once you obtain x dot, let you introduce time equal to 0. And I hope, okay, I hope you can have this second equation as in equation number 14 for the x dot 0. Okay, and it seems to be omega d multiplied with the big X1 minus psi omega X2. And once you obtain the big X1 and big X2, you can introduce equation number 15 back into equation number 10. Okay, so that now equation number 10 will be something like the equation number, oh, I'm sorry, it's not 16. 16 is the one that I use a phase angle. In fact, you can introduce equation number 15 into equation number 10. You can obtain equation number 16 prime, for example, and I hope you can have the form like this, right? E to the power minus psi omega t, and then you have the x0 dot plus psi omega x0 over omega d multiplied with the sine of, I just introduced equation number 10 for you. So let you do it yourself. You can have this as well. Equation number 16 prime is depend on the form of the equation you would like to have, whether you would like to have the phase angle form as equation number 16, or you just would like the term like the sine and cosine function, the summation of both of them. You write down equation 16 prime. Okay, it depends on which one you like. Both of them, in fact, they are the same. They are the same quantities, the same value, but look at the form, they look different. Okay, so this is what you and I have discussed so far. At the end, you see, we can have the solution of x from the start value first, right? From equation number 1, the free vibration. We start from equation number 1, the free vibrations. We try to solve this one to get the solution of x, where x is non-trivial. We are not looking at x equal to 0. And now we can mathematically prove that if we assume the damping ratio of psi less than 1, the solution of equation number 1, the free vibration solution, take the form of equation number 16. 16 here, where the initial condition of your buildings is included in the big X and phi, the phase angle. Omega d, psi, omega, 3 of them are the building parameters. For example, psi, we already defined psi, where's it? Psi is this one. Psi is the damping coefficient over 2 mass m and omega. Omega is square root of k over m. Many times I remember this instead of omega square, right? Many people prefer to say omega is equal to square root of k over m. And psi is the c over 2 m omega. Okay. Any questions so far?
No, sir.
No? No question, right? So if you don't have questions, let me continue to explain you a bit on the free vibrations. This is the plot of a function x of time t, of course. The x-axis is the time. Let me draw for you, is the time. Maybe the unit is a second. And the, you can imagine, yes, this is the time, second, right, the unit. And the y-axis, we are talking about the vibration, right? X of time t. This is a xt. If in this case, I think if I introduce, it looks like I try to quiz my previous student about this motion. Look at this one, the initial condition. The initial condition here, I don't know where I come from, but assume it's 0.6. It looks like the building start to move with the initial displacement in the positive direction, okay? And I assign that the building have the initial displacement of 0.6 meter. Assume the unit is meter. It's moved with 0.6 meter, and then I let the building move. So it's why it's moved back and forth like this. But you see, if I provide the building to have the initial displacement 0.6 meter and I release, it should move back to the origin, right? Therefore, the movement should be something like this. Go from 0.6 and go to 0 axis. But in this drawing, this graph, it looks like even though I have the initial displacement 0.6, but once the building start to move, it's moved a little bit more further to 0.7, 0.8 to close to 0.9, and then it go back. So this one indicates that the building has the initial velocity, the slope. The slope of this curve showing this. You have the x dot 0. And in the same time, you have x 0. X 0 is 0.6 meter. X dot 0 is the slope of this time function, is of this curve. Whether it's 10 meter per second or 12 meter per second, I don't know. But it's defined by this slope. Okay? That's why the building start from 0.6 and go to 0.7, 0.8, 0.9, and then it's go back to the origin. And it's keep vibrated like the bull curves. Back and forth, back and forth, back and forth, back and forth. And every time it's moved, the amplitude. When I say amplitude, mean this one. This is my amplitude, 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 the negative amplitude, and negative amplitude, negative amplitude, positive amplitude, negative amplitude, positive and negative. You see the amplitude of the vibration is decay with time. From maybe 0.9 here, I don't know, 0.9 something to 0.5 to 0.3 to maybe 0.2 to maybe 0.1 and keep smaller, and I think it's go to zero at the end when time go into infinity. Okay, this is the plotting of one example when we introduce the initial velocity and the initial displacement to the system without any force. Remember, this is a free vibration. You never apply the force. You apply only the initial conditions. Let me look at this equation number, which number? Equation number 17, I'm sorry, 16 closely. The plotting of this comes from the equation number 16. And the equation number 16 is this pink equation, right? We are plotting this. X of time t equal big X e to the power minus per sine omega t multiplied with the sine of omega dt minus phi. Let me look the term in this function term by term. Let me first look at the big X. The big X, let me use the pink color. I'm sorry, the blue color. The big X. The big X will control something, and that is about when you see, if you look at this, in this case it's equal to 1. I think if you draw this one, touch the y-axis here and the y-axis there, you can have the big X and the minus big X. Okay? Look at this one. And it's better to draw what I call is it's very hard for me to use the color now. Can you see the yellow? I don't know. This one. Can you see the yellow curve? If I draw a yellow curve to touch the amplitude of the vibrations of my building, when the term psi term equal to 1, when the e to the power minus plus psi omega t, when t equal to 0, this term also 1, you are talking about big X and minus big X. And this is why we have the big X and the minus big X to control the vibration of the envelope of the curve. The second term, let me explain this term for you. The green term, exponential term, e to the power minus per sine omega t. This term is create the envelope, the yellow envelope to my vibrations. They control the amplitude of my vibration need to be within this envelope. Okay? So the envelope itself need to be the product of the X, big X, and the exponential term. I use the yellow, but I think maybe it's very hard for you to see in the monitor. Let's see. This is the term, the two terms, the product of the big X multiplied with the e to the power minus per sine omega t, create the envelope to my building, control the vibration within this envelope. And the psi function, the last term, will be the sinusoidal, right? The psi that fluctuate up and down, up and down, up and down, up and down with time. However, you see the amplitude is reduced, is controlled by the envelope. The psi function, the magnitude of the psi function is a +1, -1, +1, -1 is always like this, right? With time. Therefore, when the times go by, the vibrations is smaller, smaller, and smaller. Who caused the vibration of my building smaller? I think it's the clean term. The clean term. The e to the power minus per psi omega t make my building vibration smaller, 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 and go to zero. The big X is just the term to create the envelope at the initial conditions. At the time t equal to zero. At the time t equal to zero, if I have very high energies to start the vibrations from the initial condition, I would have a very, very big X. And if I have a very small energies to start the vibration, my big X gonna be small too. Okay? The psi terms will explain how my building move back and forth, fast and slow. If it's go very fast or it go very slow, who control this? We found the term inside the psi function here. Let me look at this term, very important term. I use the lead now. Omega D. Omega D will control how fast, how slow my building move with time. You check very high frequency or very low frequency. It depends on omega D. And we have learned from the high school physics, I think, if you have the omega D as the circular frequency, you should know it's gonna be equal to 2 pi and FD, something like this, right? And the period TD gonna be something like this. I put the subscript D to make the term or this for the parameter who has the damping. Remember that omega D itself is defined as the omega multiplied with the 1 minus the psi square. Okay? So if you want to ask me from here to there, for example, what is the time from this location to that location? I would say this is TD. It's a one period of the vibration, right? One cycle of the vibrations. This is exactly TD. And if I know about the TD or period of your movement with time, I will know the frequency FD. And if I know the frequency FD, I can compute omega D. And if I know the omega D and the damping ratio, I can know omega. Okay? So this physical meaning of the vibration from this mathematics expression will tell us a lot of information. Sometimes we use this phenomenon, this equation, to explain how engineer can determine the stiffness of the building if they know how it's moved. or how it's vibrate. They know the frequency of the vibration. They know the period of vibration. If we can measure the real building movement, we can estimate the stiffness of the building very, very accurately. Okay? So before we go further, let me introduce you a little bit more about another term called logarithmic decrement delta. Logarithmic decrement deltas in this case is defined as the ln of the xn over xn plus 1. This is a positive amplitude. If this one I say is the x number, this is the amplitude number 1, maybe I defer, this is the amplitude x1, the big x1. This is the big x2. This is maybe the big amplitude x number 3, right? You just put the amplitude of x and find the ratio between x number 3 over x number 2, or x number 2 over x number 3, sorry. X number 2 is larger, right? X number 2 over x number 3, or x number 4 over x number 5, and you take the ln of this ratio, you will get what we call the logarithmic decrement delta, and this logarithmic decrement will be approximately equal to 2 pi per psi. Why is equal to 2 pi per psi? Let me, do I have the proof of this? Maybe not. Okay, but it is not so difficult. Okay, let me try to explain you a bit on this. To compute this one or to prove this one, you can draw that if I draw x number n could be equal to x e to the power minus per psi omega maybe time at n and psi of omega dtn plus or minus 3, something like this, right? Remember this one, I'm talking about the positive amplitude. It will have the amplitude will happen here and there whenever the psi function equal to exactly 1. Therefore, the term here equal to 1, no doubt, because you're talking about the amplitude, and amplitude is occur when psi equal to 1. And I can write down x, the amplitude when x equal to n plus 1, the next amplitude, the same function, except the time is t n plus td multiplied with 1. Do you agree with me? The time have to increase from x number 2 to x number 1, x number 3 with this amount. Look at this. When you go from this to that, you plus TD. TD is the period of vibration. Okay? So that's why you can have the TD in this equation. Okay, now you have to take the ratio of this. You put x over x number 1, the big X will cancel each other. N plus 1. You would have something like this, I believe. So psi omega TD, and this one gonna be plus minus, you divide, it goes up, right? The coefficient of the power will sum together. I think it's gonna be plus. Okay. Okay. Once you have this, you just take the natural logarithmic logarithm of this ratio. You can have 2 per sine t, right? So the ln of this, oh, I'm sorry, xn n plus 1 gonna be something like the omega td. And now you know that omega, td is what? TD is omega d over 2 pi, something like this, right? This one is omega d over 2 pi. I'm sorry, is could be 2 pi over omega d, something like this. That's why you can have approximation is equal to 2 pi per sine. When I say approximation, this comes from what? This becomes is come from omega is assumed to be approximately equal to omega d. If I assume like this, the logarithmic decrement delta can be approximately equal to 2 pi per sine. Why we can assume that omega and omega d very close? Let me explain you a bit about the Liao building. Maybe it's better time, it's a time that I move to the Liao building. At the end, okay. Okay, this is damping. You see, this is where I come from. Okay, is the experiment in, I think it's not in England, right? In many countries, in European country, in Europe, they measure the damping ratio of their building and plot the real damping, okay, against the height of the building. What they found, you see in these figures, most of the building has the damping ratio less than 10% for sure, less than 10%. And almost of them within 2-3%, 4%, or maximum is 5% at most. It's only very special building or structure have the damping greater than 5 in terms of percent, the damping ratio. Therefore, I will discuss about this later. Let me go back again. Where's it? Okay. You see, if the damping omega d is defined as the omega d equal to omega square root of 1 minus per sine square. Let me compute for you if the per sine is equal to 10%, right? The maximum damping is 10%. So let me start with this. 1 minus 0.1 square equal this, okay? Square root of this equal to this. 0.995. So my omega d can be equal to 0.995 of omega. I already used a very high damping ratio, 10%. And you see from the experiment that they have measured the real building damping ratio is like most of the time 3%, 4%, 5% at most. But I use 10%. And I found even though it's 10%, The omega D is almost the same with omega. The difference between omega D and omega is only 0.5% only, less than 1% the difference. That's why the assumption that omega close to omega D is often adopted in our civil engineering cases. Many buildings, many bridges are assumed that the omega and omega D are the same number because they are both very close. But you cannot use this assumption for the mechanical engineer who design a car or a vehicle, or the aeronautic engineer who design the spacecraft. Their damping ratio is very high sometimes. It's maybe 30%, 40%. I'm talking about the vibration of the car. The vehicle, the car, the passenger car, the bus, those damping are designed by the mechanical engineer so that the feeling of the passenger inside the car will feel very comfortable when you drive the car over a very large low surface, or if you go to the big bump, you still feel very, very soft or very smooth feeling. Such kind of thing have to dealing or have to design with the car suspension having a very high damping ratio like a 20-30% or greater. But in our case, our building, if you have the initial condition, initial displacement to your building, if we keep move like this, and it take some 10 seconds, 20 seconds to go down, the damping is very, very small in our structure. It's not like the car. If you check your car, if you move like this and then it stop very fast. I press my car like this, my car will bump up and down, not like this, but it's deep and then it stop. Due to the damping ratio of the car suspension is very high. Compared with our structure, the building, the bridge, we have very, very small damping ratio in our structures. Okay, that's why many cases or in many situations, you can assume the omega and omega D are the same number. And that will simplify your computations. As in equation number 18, right? For the logarithmic decrement for the delta. Let me move a little bit. I try to finish this one first. The first case of the damping ratio less than 1, right? Under damped system. Okay, we have the vibration like this. And we found some more interesting thing in which the movement of our building will go back and forth, controlled by a psi function. As in equation number 16, right? The psi function will force my movement to go back and forth, back and forth, back and forth. And imagine if my damping equal to 0, what happened? If my damping ratio or damping C equal to 0, your green term, exponential term, become 1, become a unit. And then your building will keep moving as a psi function back and forth to the maximum movement of the big X and to the minimum movement of the minus big X, X minus X, X minus X, X minus X forever, non-stop. This is because you don't have the damping. Without the damping, you will shaking like the pendulum of the clock. You keep shaking like this forever. Okay? When we introduce the damping, into the system. The building starts to slow down and slow down, not slow down, so smaller and smaller in terms of amplitude with time. And then it stops. This is the effect of the damping term, the clean term. They make the amplitude, the envelopes smaller, smaller, go to zero with time. So if I want to make my building stop faster, what should I do? I want the building to move like this and then stop. I don't want my building like this. It take maybe how very long time before it can stop. No doubt. You need the clean term to be a very high coefficient. And that come from the precise, a product of precise with omega. The damping ratio and the circular frequency. If my building, the stiffness and the mass is fixed, omega is fixed too. Because omega is the square root of K over M. Therefore, what I have to do is to play around with precise. I have to find a way to increase precise to my building. Unfortunately, we have a fixed number of our structure, our building. For example, the concrete building, reinforced concrete building, most of the design code prefer the engineer or the designer to use the damping ratio not greater than 3%. Okay, 2-3% at most for the reinforced concrete building. But if you design your building using the steel structure, if you use a wide flange, the H columns, steel beams, steel shear core, such building or steel structure buildings, the design codes recommend or suggest to use the damping ratio of 1 or 2% at most. So the steel structure has smaller damping ratio than the reinforced concrete building. But even though I use a reinforced concrete building, the damping ratio is still very low. It's only 3%, 2-3%, very small number. That's why my building still keep vibrating like this and takes more time to stop. And the effect of this small damping building under the earthquake, they will shake a lot. If one can find a way to increase the building damping, you can expect the movement of your building to be smaller than the normal building. That's why in many countries, there's some invention on what they call the damper. They put the damper into the building, install the dampers in the building to make the building more and more higher and higher damping ratio, so that you can make your building to stop very fast or faster than a normal building. Under the earthquake, under the wind, you will see later, the effect of the damping is very, very high effect or very significant on the vibrations. Therefore, we will keep the discussion of the damping again once we discuss about the force vibration in the next chapter. But today, before I stop and okay, the frequency and the periods is like this, right? So it's no doubt no problem for you. But let me a little bit explain you about the damping. Otherwise, you will feel how it's come from. Let me go back to this equation of motion. Okay? Equation number 1, mx double dot plus kx, the pink and the red terms have no doubt because it comes from the law of physics. According to the second law of motion from Sir Isaac Newton. But the blue term, we assume to be the term Cx dot like this. Why we assume the Cx dot? I try to provide you a little bit information on this so that you can have a little bit clear idea why we do like this. Okay? One of the possibility that the engineer will imagine about the damping is about the friction. You know the friction? If I draw you this, the mass and the spring put on the floor, and the mass on the floor have some friction. I don't know. Okay, you have some friction. So that friction you try to prevent your building to move or prevent your structure, the mass M to move freely, right? And try to make the mass to stop. It will try to dissipate the energy from your system to the heat of the friction surface. So your energy inside your system will be smaller due to this friction force and stop the vibration. This friction force can be one of the damping force. And mechanical engineer, they use a lot of the friction damping. Sometimes they call Coulomb damping. I'm not so sure how to spell the Coulomb. Coulomb. You find yourself, I'm not so sure it's a Coulomb or something like this. But in fact, it's a friction. This is a column, right? So let's check my English, my spelling is not correct.
Sir, I think it's B at the end instead of N.
Instead of N, you have the E?
B, B,
B.
B. Yes, sir, B.
This one? Okay, thank you. So we found if I define the term like this, the damping coefficient here, let me draw you this. You can find from many textbooks, right? You have equation of motion like this. If the C is the friction coefficient, is the term could be something like this. I think is the x dot over absolute of x dot multiply with the normal, or is the mg. This is the normal force on the friction surface plus the kx. I'm sorry, kt, something like this. And this one, this term, the friction term, become a nonlinear. Once it becomes nonlinear, it's very difficult to obtain the solution as we have discussed from equation 1 to equation 16 as today's discussion. No, it's more difficult, much more difficult. If I represent or formulate my damping or assume my damping term as a friction damping. So what type of damping could be very practical or easy or easiest to use for our building? Of course, our building damping is come from a micro crack in many parts of the building in the column during the vibrations. We cannot see the clacking like that, but we assume there's some small clacking we cannot see, and that dissipate the energy of vibration. However, to model that, we are looking for a simplest idea or simplest mathematical model to represent the damping term. And the simplest one is called this. It look like I am, where am I? Have the same system, the mass M, stiffness K, but now let you move everything under the water. Assume you have the water. Your mass is submerged in the water. If you move the mass back and forth, there's some, it's not the friction, there is some resistance from the water. Try to prevent your mass to move freely, and then they will stop your movement due to the resistance from the water or the liquid. Assume this. If this one is the water, you can test in your house or your home, very simple, and dip your hand finger into the water. And if you drag your hand finger under the water, okay, this is the water, you dip your hand finger like this, and you move your hand in the water. What you feel is something like this. If I move the finger to this direction, I will use some resistance, try to resist my movement. And if I move this direction, the force will acting on the opposite direction of the movement of mine. Okay? So these directions is depend on the direction of your velocity. If your velocity is plus or positive, the resistance force from the water acting on your hand finger will be in a negative directions. On the other hand, if your movement with the velocity is the negative directions, the direction of the force, the resistance from the water will be in the positive direction, in the opposite direction to your velocity movement, always. We call this one as the viscous damping, not the friction or Coulomb damping, but the viscous damping. The viscous damping has the term Cx dot. And the wonderful thing from the viscous damping is the force is proportion to the velocity. If I move my hand finger faster, I will feel the force larger. Unlike the friction or the Coulomb friction damping, if you move the mass that have the friction on the floor, on the table, if you move faster, the friction force remain the same. Remain the same. That's why I have to divide by the absolute of x dot, because it's not proportion to the velocity. You increase the velocity of the movement of the mass, the friction force still the same. It's constant. It's just the normal force, the mg multiplied with the friction coefficient. Okay? So it's a non-linear term is not good. The linear term is make our system to have the very, very simple form of mathematics. And for example, if my system or my building has the displacement 2 times the movement of my building will have 2 times. Okay, for example, if I let my building to have a 1 meter and let it go, if you move like this, right? If I move 2 meter, it will go 2 times, that's it. Everything multiplied with 2. The same thing when you go with the force. If I apply the force 10 kilonewtons and my building is moved like this, if I apply the force, the same force function, but the magnitude increased 2 times to 20 kilonewton, it will go exactly with the previous motion, but the amplitude is 2 times. Because this is our system is the linear system. You see, that's why I think every civil engineers prefer viscous damping uh, physical model or viscous damping representative of the damping term of that building, because it's very simple. It's make our building system in terms of mathematics become a linear system, and it's easy to be solved by hand or by computer. Okay, I would like to stop here for today's lecture. And if you have a question, this is the time. Maybe just, oh, it's already noon, right? 4 5 minutes, if you don't mind. Any questions so far?
Yes, sir. I have one question.
Okay, please.
Sir, we know that many factors governing the natural damping.
Mhm.
Sir, I want to know uh, in a real building which factor governs the major natural damping component.
You mean the real building?
Yes, sir. Uh,
Oh, okay.
which factors
Okay.
which
At
factor
least,
contributes most to the damping?
at least from the design code, the you can observe them and notice that the type of the structure have a very significant on the damping ratio. As I explained to you before, the steel structure has a lower damping ratio than the reinforced concrete building structures. And even though this phenomenon there's some research paper talking about they will use some member to generate the damping. For example, in New Zealand or in Australia, but mainly from New Zealand, they design some member, reinforced concrete member, to have a very low strength, so that during the earthquake, this beam will sacrifice by cracking, a lot of cracking, yielding. And they compute the contribution of the cracking of and yielding of the steel member, the beam, a big beam. For example, we are talking about a 10-story building. If I'm introduce only one beam to be cracked or yield, that will contribute to my damping ratio less than 0.01%. Very small, right? I'm talking that we need maybe 100 of the beams like that. 100 of the beams that sacrifice themselves to have the yielding, cracking during the earthquake, so that your damping ratio can increase maybe 2% or 3% or 1% at most. Therefore, if you ask me which part of the building contribute or the main or dominate the damping characteristic or behavior of the building, I think it's very hard to answer, because all of them have very small contribution. I don't know, maybe 2%, 3% is not occur inside the building. Some people explain that actually the damping ratio of our building come from the foundations. Some of the researchers saying so. Because in the foundation, you see, there's an interaction between the soil and the footing and the piles. So they can dissipate some energy under the ground, our building, tall building. Maybe this can be a major part of the damping, I think. And I'm sorry I don't have so clear information about this, but to me, inside the concrete structure contribute very, very small to the damping ratio to our building. Maybe from the foundation is very high damping. So the 2-3% as the design code suggests or recommend for the reinforced concrete building, maybe 70-80%, 80 or 70% is a portion from the foundation, dissipation or damping. I don't know I answer your question or not, but please use a Google or research a little bit more on this. Your question is quite interesting, but I think it's still not clear yet to engineer society or civil engineering knowledge, which part of the building contribute a lot on the damping ratio yet. Maybe it can be one of your research topic if you like. And it look interesting to me too. I'm sorry to cannot answer you a good response on this.
Thank you, sir. You give good information about my question.
Okay. Any other questions on the discussion so far? Okay, if you don't have, I would like to stop or end the class here and hope to discuss with you again this coming Thursday, 10:30, okay? Okay, have a good day. Goodbye.
สวัสดีครับ